What we want to do now is start looking at series and parallel circuits. Alright, so we're going to talk about series and parallel circuits. These are the two basic type of circuits that involve two or more resistors. Alright, so you can have circuits that have two or more resistors, two or more voltage sources or whatever, but we're going to mostly focus on one voltage source and two or more resistors. Alright, so one voltage source and two or more resistors. Alright, okay. So before we get started talking about that, I do need to mention one thing, and that is, in the last video I said we were going to talk a little bit more about what direct current meant. Alright, direct current. And what direct current is, it's the kind of current produced by your battery. And let's say I just have a loop of wire here, and I have a light bulb here, and my light bulb is shining because I've connected the complete circuit here. And what the direct current means is that the current just simply flows one direction all around the loop. Alright, so the current just keeps moving in one direction. That is opposed to alternating current, or AC current, which is what your wall outlet gives. And what that means is, if I have an AC source, and we denote it like this, alright, if I have an AC source and I have a light bulb, then for a little bit of time current is pushed out this direction, and then it reverses direction, and then it's pushed out this direction, and then it gets pushed out this direction, and then it just keeps on reversing, right? And so this is what we call AC. So most of our circuits that we're going to look at in this chapter, we will specifically focus on direct current, but I just wanted to make that distinction so that you understood what your textbook and other sources might be talking about when they use the term DC and AC current. All right. Okay, so let's talk about the series case. Right? Let's talk about the series case. So a series circuit involves two or more resistors and only one path for the current. So two or more resistors and one current path. In other words, there's no place for the current to branch out of. So the current just flows through one individual loop. And a very simple circuit might look like this. Alright, so here's my battery, and I may have a resistor right here, and another resistor right here, and they just form one complete loop. So my current starts here, flows through here, flows through resistor, the first resistor, then through the second resistor, and then back into the battery. Alright, and I can label this resistor 1 and this resistor 2. Now if we were to look at this in the pipe flow model that we looked at in the last video, this would be dam 1 and this would be dam 2, and both of these dams are going to work together to limit the current flow. Alright, so both resistors work together to limit the current flow. And so what that means is that the total resistance in the circuit is just going to be the sum of R1 plus R2, whatever it is. Right? So the total resistance in the series circuit is just going to be whatever the total first whatever the first resistance plus the second resistance is. All right, that'll be the total. So let's just do a quick example here. So let's say I have a voltage source of, let's say, 12 volts. All right, and then I have a resistor here, and then a second resistor here, and I hook it all up. And let's say that R1 has, let's say that these are both 24 ohms. Alright, so these are both 24 ohms. So R2 is 24 ohms. All right, so I can ask two questions here. Number one, what is the total resistance? And two, what is the current flowing through this circuit? All right, so those are my two questions, and let's answer each one of them in turn. First, my R total is just going to be R1 plus R2, as we said before, and R1 again is 24 ohms, and R2 is 24 ohms. So my total resistance is now just going to be the sum of these, and that's going to be 48 ohms. All right. And so now what about the current? Well, this is the total resistance in the circuit, and so when I apply Ohm's law, V equals IR, when I apply this law to a total circuit, then I have to use R total. All right. I can apply Ohm's law to each individual resistor as well, but in the case of finding the total current in the circuit, I have to apply the total resistance, right? And when we only have one voltage source, then your battery is just your total voltage. All right. So how do we solve this? Well, remember that we solved this last time. We said our current, if I divide both sides by R, is just going to be V over R, and that gives me 12 volts divided by 48 ohms, and that happens to be 0.25. So this is going to be 0.25 amps, or a quarter of an amp. All right. Okay. Now, one thing to note that a series circuit displays, one characteristic of a series circuit, if we go back here, that the current will be the same everywhere in the single loop. So when you have one loop, I is the same everywhere. All right. So if I measured, and by the way, we measure current with things called ammeters, but wherever I put my ammeter, I could put it here, I could put it here, I could put it here, or I could put it here, and my ammeters would give me the same reading in every single case, because in a single loop the current will be the same everywhere. All right, so that is a distinguishing characteristic of series circuits. Now let's look at the parallel case. All right, so let's look at the parallel case. All right, now I'm going to draw my battery a little bit different. Let's draw an actual 12-volt battery here like you might have on your car. All right, so imagine I have some wire coming off of my battery this way, and some wire coming off of my battery this way, and we'll make this the positive terminal and this the negative terminal. So imagine that the negative terminal is held at 0 volts and my positive terminal is held at 12 volts. What that means is I have a potential of 12 volts across the two wires. Right? So I have a potential of 12 volts across the two wires. Now let's see what happens if I insert a resistor right here across the two wires. Well, if I have a potential of 12 volts across this resistor, then I have a complete loop from my battery, and this will cause the current to flow. All right? But what happens if up here I insert another resistor? Let's call this R1 and this will be R2. All right. So what happens now if I have another resistor in here? Well, you can hopefully kind of get a sense of what might happen here. So some current is going to leave the, I'll draw it on the outside here, it's going to leave the battery, and then when it comes to this junction right here, it will split off, and some of it will go this way, and some of it will go this way. And then the current that went up will go through resistor 2 this way, and then down this way, and the current that went through R1 will meet up with the current that went through R2 right here, and then the total current will come back down this way. All right? But what is that total current? Right? So what is that total current? That's the question. Well, we can kind of get a sense of what's going on here. How much current goes through R1? So the real question here is current through R1 and the current through R2. Right? These are the questions. Right? Well, again, apply Ohm's law to each individual circuit element. To each resistor. Alright, so if I redraw my diagram, and I'll draw it just a little bit differently and use our other circuit notation here. And here I'm going to have my battery, and I'll draw it off to the side here so I can do some math. But here I have my battery, and here I have one resistor. And then up here I have another resistor. Alright, so the thing to note here is that both resistors, we'll call this R1 and this is R2, both R's feel all of V, right? Whatever the voltage of your battery is, both resistors feel all of those because this section of wire and this section of wire, the potential difference between them is the same. So both wires, or both resistors, feel the exact same potential difference. And so what you can do is calculate the current through R1 and then do the same for R2 and then add both currents up to get I total. Alright, so I calculate the current that would flow through R1, and we'll call this I1, and then calculate the current through resistor 2, call it I2, and then when the two currents meet here, the total current that then flows into the battery must be the sum of those two, and then that's also the same current that flows out of the battery after the current's been recycled, and then of course here they branch this way. Alright, and so let's just do a quick example of this. Let's use the same values that we had last time, and let's use 12-volt battery and resistances of 24 ohms. Alright, and there's nothing, well, there is a special case where your resistances are exactly the same, but this process works for any value of your resistors. Okay, the process works for any value of your resistors. So let's label this R1 and this will be R2, and what that means is that I1 will equal V over R1, I2 will equal V over R2, and so this is going to be 12 volts divided by 24 ohms, and I2 will also be 12 volts divided by 24 ohms, and 12 volts divided by 24 ohms is 0.5 amps. And so in both branches here, in both loops, we have 0.5 amps running through them. So when, again, they meet right here, the total current running through there is just going to be the sum of those, which turns out to be 1 amp. Alright, so let's see exactly what this means. Some consequences of this process, some observations. Number one In a series circuit, the resistors add to increase the resistance. Okay? So they add to increase the resistance, or the total resistance. In a parallel circuit, the total resistance decreases, right? So, and what that means, let's kind of review what this meant. The in the series case, we had 12 volts and two resistors, one of 24 ohms and 24 ohms, and we found that our current dropped to 0.25 amps. In the parallel case, we had 12 volts, 24 ohms, and 24 ohms, and our current was 1 amp. And so what that means is that in the parallel case, our total resistance was effectively smaller. All right? So this had a smaller total resistance. Okay? So our parallel case has a smaller R total. And if you want to calculate what the resistances are going to be in both the series and the parallel case, all right? So how to calculate our total in the series case, it's just going to be the sum of all your resistors. And that's what we already said, but you can have more than two resistors, so, you know, plus however many resistors you have. And in the parallel case, we won't derive this formula. I'm just going to hand it to you, all right? And your book does too. It doesn't actually derive it for you. But a detailed analysis shows that the parallel case, the total resistance is found by taking the reciprocals of all your resistors. So 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus however many other resistors you have in the parallel case. All right, and we can kind of reverse engineer and see how this formula works. Let's apply this to our parallel example. All right, so in our parallel example, we had 12 volts, and we had a current of 1 amp. And what is the total resistance? All right. Well, we can find it from Ohm's law, V equals IR. And to solve for R, I just divide both sides by I. And R is going to equal 12 volts divided by 1.0 amps. And that gives me a total effective resistance of 12 ohms. All right. And we want to verify the formula, R over 1 over RT equals 1 over R1 plus 1 over R2, and show that for our case, the total resistance is also 12 ohms. All right, so we want to show that these two analyses agree, one using Ohm's law and one using our resistance formula. So let's take 1 over R total and take the inverse of or the reciprocal of 24, 1 over 24 ohms, plus 1 over 24 ohms. And now we need to do our fractional analysis. So the way fractions work, find a common denominator, which these are common, they're the exact same, and then the numerators just add. So I have 2 over 24 ohms. And now that I have this, I can just take the reciprocal of both sides, right? I can take the reciprocal of both sides, and I get RT equals 24 ohms over 2, or 12 ohms. All right. So in both cases, one using Ohm's law and one using the inverse resistance formula for parallel cases, they give me the exact same result for the total resistance in the circuit. And what I mean by that is that this circuit, all right, this circuit right here is no different than a circuit that looks like this. All right. As far as the battery is concerned, these circuits are identical because the same amount of current is going to flow. It's going to need to push out the exact same amount of electricity in both cases. All right. So there you go. There's a couple examples of using series and parallel circuits, and we will see you next time.